Welcome to the first video of real analysis. So we shall begin the real analysis by uh, introducing, or it is not introducing, just recalling the one of our favorite or commonly used set, that is natural numbers. So how we denote it? Say we denote it by n. So it's a set of all natural numbers starting from say 1, 2, 3, and so on. There's a set of all natural numbers. Now this set n is characterized by some properties. We shall call them as Peano's axioms. So what are these axioms? So the first one says there exists a particular element denoted by 1 in n. And second one says, so there is a function sigma from my set of all natural number to set of all natural number called successor function called successor function, which assign to each n belongs to n an integer sigma of n belongs to n and call it the successor of n. That is, for each n belongs to n, we assume sigma of n belongs to n. That is, where sigma of n is successor of n is nothing but n plus 1. That means sigma of 1 is equal to 2, sigma of 2 is equal to 3, and so on. Yeah, you can observe that this successor function is 1 1, but it is not onto. Not onto because it is sigma of n is equal to 1. That is, for this 1 in the codomain, there is no element in the domain such that sigma of n is equal to 1. So it is not equal to 1 for any n belongs to n. Therefore the sigma is not 1 2. It is not onto, but it is 1 1. It is 1 1. The third condition, or the third property is, if s is contained in n, s is a subset of n such that 1 belongs to s, 1 is in s, and sigma of n belongs to s for any n belongs to s. That means whenever you take a number from s, its successor is always in s. Moreover, 1 is in this. Then what must be s? S must be equal to n. S must be equal to n. So these are the three properties which we call it as the successor of n. Successor of n. Okay, wait a second. Okay, now, so from this set of all natural numbers, we are moving to the next set, that is nothing but z. Z. So we call this as set of all integers. Set of all integers. That is nothing but 0 plus or minus 1 plus or minus 2, so on. And from this we are moving to the next set, that is it's a set of the form p by q, where p comma q belongs to z and q not equal to 0, and we call this set as rationals. This is a set of all rational numbers, or nothing but a set of all numbers of the form p by q, where both p and q are integers, q not equal to 0. Okay, so now we get a question, like while solving. So from natural numbers we move to the integers, from integer we have moved to the set of all rationals. Now So while we have working with natural numbers, integers or irrational numbers, we come with the problem that x square equal to 2. Now the question is whether this is solvable in n or z, or let me since n is contained in z, z is contained in q, the question will be whether this x square equal to 2 is solvable in q. That means whether there is an x belongs to q such that x square equal to 2, x square equal to 2. Now suppose there exists some s belongs to q such that my s square equal to 2. Now since s belongs to q, s will be of the form some m by n, where n not equal to 0, where m and n are integers. Now since my m and n are integers, we shall assume that m and n have no common factor. That means if m is some multiple of some k and n is multiple of some k, then that we can cancel that k. That means m and n have no common factor. M and n have no common. But it says here this s satisfies s square equal to 2. That means m by n whole square is equal to 2. Or this says m square is equal to 2 into n square, now this implies m square is even, but but then this m square even implies m is even, now m is even, so we shall take m is equal to some 2 into k, now my equation, that is m square equal to 2n, it becomes 2k whole square is equal to 2 into n square, now this is nothing but 4k square equal to 2 into n square, and that is nothing but you can cancel 2, that is 2k square equal to n square. Now this implies n square is even, which implies n is even. Now observe, we have m is even as well as n is even, but we assumed that m and n have no common factor. Since m and n have no common factor, m and n cannot be even at the same time, because if it is a even, then it's a multiple of 2, so this says m and n have common factor 2, and it's a contradiction, therefore my assumption that this x square equal to 2 as a solution, in q is wrong. Therefore x square equal to 2 is not solvable in q. It's not solvable in q. Now similarly, if I go with the equation, that is x square equal to p, where p is a prime. Now whether this is solvable in q, so if I go with the same method, by using the property of prime, we arrived that this is not solvable in q. That means if I list all the rational numbers, say these are the rational numbers, then these rational numbers contains natural number as well as integers, but it says still my x square equal to p is not solvable in this. That means there are some numbers which is not rational, so there are some numbers which is not rational. Therefore it says my q has some gaps, or q in my number system have some gaps. So that means if I write all my rational numbers in a line, these rational numbers contain natural number as well as integers, but in this line there are some gaps, there are some gaps. So we shall call these gaps as irrationals, irrationals, irrationals. So irrationals are nothing but they are numbers which are not rationals, so we shall denote it by q complement, q complement. Now you from this q and my q complement, that is we are taking the union of rationals as well as irrational, we shall denote it by r, that is set of all real numbers, set of all real numbers. Okay, now moving forward. Okay, so to deal with this set, that's a set of all real numbers, we need some properties, or we need some tools, so to define these tools we shall just define some terms, in the uh, or in general definition, we shall define some terms in a general space, not exactly at a real number system. We just define some tools in a set for that. So let S be a set. Say a relation less than on yes is called an order on yes. A relation less than on S is called an order on S if it satisfies the condition. The first one is trichotomy, trichotomy, trichotomy. And this condition says for any a comma b belongs to S, either a is less than b, or a is equal to b, or b is less than a. So this condition says for any a comma b belongs to S, either a less than b, or a equal to b, or b less than a, and we call this condition as trichotomy. So the condition 2 says if a less than b and b less than c in yes, that is nothing but for any a comma, okay, if for any a comma b comma c belongs to yes, a less than b, b less than c, then it says a is less than c, we call this condition as transitivity. So if a set yes, okay, if a set yes with this relation satisfying these two conditions, that is trichotomy and transitivity, then this relation less than, we call this relation as order on S, order order on yes. Now this set yes with this order, we call this as ordered set, we call it as ordered set, we call it as ordered set, ordered set, ordered set. Now moving. So whenever I use the term S comma less than, the meaning is less than is an order on yes. Now what is order? S is a set, less than a relation less than satisfying two condition, trichotomy and transitivity. What is trichotomy? Trichotomy says for any a comma b belongs to S, either a less than b, or a equal to b, or b less than a. And transitivity says whenever a comma a b c belongs to S with a less than b and b less than c, then a must be less than c. Okay, so the example for a ordered set is, consider the S as set of all natural number, and my usual less than. Now observe that this n is a set and less than is an order. Less than satisfy trichotomies because for any a comma b belongs to n, either a is less than b or a equal to b or b less than a, b less than a, or the second condition to be transitivity says whenever a less than b and b less than c, a is always less than c, a is always less than c. So with these two properties, my a, this less than is an order on a, order on n, and hence this n comma less than is an ordered set, is an ordered set. Now in this ordered set, we are going to define some more using this ordered set. We are defining some more terms. Okay, now let s comma less than be an ordered set, be an ordered set. Now you know what is s less than, it says it's an ordered set. Now you know what is the meaning and what is the definition of ordered set. If not, just go back and replay the video once again. Okay, now here S is an ordered set, and and E be a subset of yes, E be a subset of yes. Now an element U belongs to yes is said to be an upper bound, is said to be an upper bound of E. An element U belongs to yes is said to be an upper bound of E if E is less than or equal to U for all E belongs to E. An element U belongs to yes is said to be an upper bound of E if this U is greater than or equal to E, every element of E. Now note that we have taken this U from yes. Now this is U may be in E or may not be in E, but U is in yes. It is said to be, this U is said to be upper bound provided this U is greater than or equal to every element of E, every element of E. Now the next one is an element L belongs to yes is said to be lower bound, said to be a lower bound of E, a lower bound of E if my L is less than or equal to E for all E belongs to E. That means L is less than or equal to every element of E. Now similar as you seen in the upper bound, U is also element of S. That means U may be an element of E or may not be, but to say L is a lower bound, L must be less than or equal to every element of E, every element of E. Now if E has a if E has an upper bound, then that is in an ordered set, a subset E is a subset of yes if this E has lower bounds, if this as E has lower bounds, and then we say that E is bounded below. If this E has lower bound, if E has lower bound, then E is bounded below, then E is bounded below. If this E is, if E has upper bound, then E is bounded above, Okay, if E has both upper bound as well as lower bound, then we call that A is bounded. E is bounded. Okay, now you have seen that this n is a ordered set. It's an ordered set. Now take E is equal to 5, 10, 15 and 25. and 25. That means this E is a subset. It's clearly a subset of natural number, and moreover this set contains exactly 4 elements, that is 5, 10, 15, 25. Now observe that take u is equal to take u is equal to 27. Whether this 27 is greater than every element? Yes, 27 is greater than 5, 10, 15, 25. Therefore this 27 is an upper bound of e in n. Now take 26. Yes, 26 is also upper bound of e in x. Now take 101. This 101 is also upper bound of E in N. Now just observe 25. Yes, 25 is greater than 5, greater than 10, greater than 15, equal to 25. That means this 25 is greater than or equal to every element of E. Therefore, it is also an upper bound of E in N. Now take 17. Whether this 17 is an upper bound? If this 17 is greater than 5, greater than 10, greater than 15, but it is not greater than or equal to 25. Therefore, this 17 is not an upper bound, not an upper bound. Now check with 0. Now this 0 is less than or equal to 5, 10, 15, 25. That means this 0 is less than every element of E. Therefore this 0 is a lower bound of E in N. Now go with now 0 is a lower bound of 0 is a lower bound, but we know that this is a wrong statement. An element must be an element of N, but 0 is not an element of N. Therefore this is wrong. Now check with 1, whether 1 is a lower bound of E in N. Yes, 1 is less than or equal to 5, 10, 15, 25. Therefore 1 is a lower bound of E in N. Now 2, yes, 2 is also lower bound. Whether 3? Yes, 3 is also lower bound. 4? Yes. 5? Yes. What about 6? 6 is not, because 6 is greater than 5. Therefore this 6 is not a lower bound. Whether 14? 14 is less than 25, less than 14. What about 10 and 5? It is not less than 10 and 5. Therefore this 14 is not a lower bound. What about minus 6? It is similarly as 0, minus 6, all are not an element of N. So it is not to say it's a lower bound. The element must be from the ordered set, that is yes. That is, in this case it is from N, but here 0 minus negative integers are not an element of N. Therefore then no need to say whether they are lower bound or no, lower bound or upper bounds. Okay. Now moving further. Okay, wait a second. Move further. Now, as N is an ordered set, this natural number, that is Z, is also ordered set. Now clearly N is a subset of Z. Moreover, whether N is bounded above. Now give me an element in Z which is greater than every element in N. Give me an element in N, Z, give me an element U belongs to Z, such that my U is greater than or equal to N for all N belongs to N. Now such an element does not exist. Therefore my N has no upper bounds. In Z. Therefore my N is not bounded above. Now what about lower bounds? Now clearly 0 belongs to Z and 0 is less than or equal to N for all N belongs to N. Moreover, 0 is clearly less than N for all N belongs to N. Therefore 0 is a lower bound. What about 1? Yes, 1 is also less than or equal to N for all N belongs to N. Therefore 1 is also lower bound. Now Here we can go with 0, -1, -2. Now take any minus, take say -10. -10 is also less than n for all n belongs to n. Therefore, -10 is a lower bound. Lower bound. Therefore, we can say that this n is bounded below. N is bounded below. Bounded below. Okay. Yes. Yes. Now. Now, just recall what is ordered set. Okay, what is ordered set? What is upper bound and what is lower bound? With one example. Okay, now moving further. Now let again s comma less than be an ordered set, and E is a subset of yes. E is a subset of yes. Now an element A belongs to yes is said to be supremum, or we call it as least upper bound. Least upper bound of E. An element A belongs to S is said to be least upper bound of E if my A is an upper bound. E is an upper bound of E. A is an upper bound of E. A is an upper bound of E, and if B is any upper bound, B is any upper bound of E, then my A is less than or equal to B. This is see, A is an element of an element A belongs to S is said to be supremum or the least upper bound. The name itself says it is least upper bound. It says if the element that the A must be an upper bound of E, and A is an upper bound of E, and A is an upper bound of E, and if there is any other upper bound, this A must be least, that is A is less than or equal to any other upper bound. Then we call A as the least upper bound of E, or the supremum of E over S, supremum of E over S, and we denote this A by supremum of E over S, supremum of E over S. Now the next one, an element say yeah, we shall go with A. An element A belongs to S is said to be infimum or greatest lower bound if greatest lower bound of E, if A is a lower bound. First of all, that A must be a lower bound of E, and if B is any lower bound of E, if B is any lower bound of E, then my B must be less than or equal to A. B must be less than or equal to A. The name itself is the greatest lower bound. That means A is a lower bound, then A is lower bound, and it is the greatest among all the lower bounds of E. A is the lower bound of E, and A must be the greatest among all the remaining lower bounds of E. Then we call this A as infimum, and we denote this by A is equal to infimum of E over yes, infimum of E over yes. Now we have seen in in that is in the ordered field Z, sorry, in the ordered set Z, we see that n is clearly subset of Z, but this n is not bounded above, so this n has no upper bound, no upper bound. Since to get a supremum we need an upper bound, since n has no upper bound, n is not bounded above, this n has no supremum, no supremum in Z, no supremum in Z. But n is bounded below, in Z. And what are the lower bounds? Yes, we know that 0 is a lower bound, 1 is a lower bound, -1 is a lower bound, -2 is a lower bound, -3 is a lower bound, and so on, because these numbers and so on, these numbers are less than every element of n, therefore these numbers are lower bound. Now in these numbers the greatest one is 1, therefore infimum of n over Z is equal to 1. That is, 1 is the greatest lower bound of n. 1 is the greatest lower bound of n. Now we shall take an example. Take the ordered field, that is q or q with say that's nothing but s is equal to q here, and take e is equal to set of all r belongs to q, such that my r is greater than 0 and less than or equal to 1. Now clearly this e is a subset of s. Now Now, note that any rational number, any rational number belongs to Q with r greater than 1 or greater than or equal to 1. Any rational number r belongs to Q with r less than equal greater than equal to 1. We can say that r greater than equal to 1. R is always greater than or equal to e for all e less than or equal to, for all e belongs to e. That means in every rational number greater than or equal to 1 is an upper bound of e. Every rational number greater than or equal to 1 is an upper bound of e. Therefore now moreover r is, for every x belongs to e, x is less than or equal to 1. Therefore this one is an upper bound. Now is there any if y is any upper bound of e in q, if y is any upper bound of e in q, then this y must be greater than or equal to e for all e belongs to e, right? Y is an upper bound, this y must be greater than or equal to every element of e, now if you observe 1 is also an element of e, because 1 is a rational number and r is a rational number between 0 and 1 including 1. Therefore 1 is also, so in particular this 1 is less than or equal to y, 1 is less than or equal to y, but what we have, 1 is an upper bound, y is any upper bound. Now this same 1 is less than or equal to y, that means for any arbitrary upper bound of e in q, 1 is always less than or equal to that upper bound. Therefore 1 is least upper bound. Therefore this 1 must be supremum of e over q, supremum of e over q. Now we shall find what's the infimum. What is the infimum? Now we have that the e is nothing but set of all, we shall just recall once again, a set of all rationals between 0 greater than less than or equal to r, rational number greater than 0 and less than or equal to 1. We have taken e is a subset, e is nothing but that's here this we have taken, it's a set of all rational number greater than 0, less than or equal to 1, now Now, now what it's clearly we can see that every number, every rational numbers in E, for all E belongs to E is greater than 0. E is greater than 0. Therefore this says 0 is a lower bound. 0 is a lower bound of E in Q. 0 is a lower bound of E in Q. Now we need to show that this 0 is the greatest. We shall show that this 0 is the greatest lower bound. That means suppose y is any lower bound, of E in Q. We need to show that y must be less than or equal to 0. Y must be less than or equal to 0. Then this 0 will be infimum. Suppose y is greater than 0. Y is greater than 0. Now observe, this says, now y is a lower bound of E in Q. That means the meaning of this is y is an lower bound of E in Q. The meaning of this is y belongs to Q such that y is y is less than or equal to E. Y is less than or equal to E for all E belongs to E. For all E belongs to E. But see, since now wait a second. We assumed that we assumed that y is greater than 0. Y is greater than 0. Second, y is greater than 0. This implies y by 2 is greater than 0, but this is less than y. Less than y. Less than y. Now see here y is a lower bound of E in Q. The meaning is y belongs to Q such that y is less than or equal to E for all every. In particularly, y is less than 1. Y is less than or equal to 1. Since 1 is an element of E, y is less than or equal to 1. Now, y is less than or equal to 1 but greater than y by 2. Now, y by 2 is also greater than 0. Y by 2 is also greater than 0. Now observe, y is an element of Q, therefore y by 2 is also element of Q. Now we got an element of Q, which is greater than 0, and less than y. What we have assumed, y is a lower bound of E. Now y by 2 is greater than 0, less than 1, and it's a rational number, that is 0 less than y by 2 less than 1. This implies y by 2 belongs to E, but we have y by 2 is less than y. What we know about y? Y is a lower bound. That means y must be less than or equal to every element of E, but we got y is greater than an element of E. It's a contradiction to the fact that we assumed y is greater than 0. It's a contradiction to the fact that y is a lower bound. We got contradiction because we assumed that y is greater than 0. Therefore my y, therefore 0 must be that means y must be less than or equal to 0. That means if any lower bound, that lower bound must be less than or equal to 0. Hence my 0 is the greatest lower bound, or infimum of E over Q is equal to 0. Infimum of E over Q is equal to 0. Now take a question. Find the infimum and supremum of set of all 1 by n where n belongs to n over Q. Find the infimum and supremum of set of all 1 by n where n belongs to n over Q. Thank you.